Hello, I am Professor Caudill, and this is our second video of physics. So let's get started. I wanted to start by reviewing what we learned last time. Um, so I did, after thinking about it more, I think I understood what we got stuck on last time. So we had a supercomputer that was computing at 10 to the negative 17 computers a computes a second. And it was basically asking how many does S happen in a day. So to do this, you have to calculate how many seconds are in a day, which is about 84,000 approximately. So, and that's, if you're doing the rough order of magnitude, that's 10 to the 6, which is a little bit off of, the computer had 10 to the 5, which is contrary to what the book was even teaching you. But then when you want to do this, it's 10 to the 6. That's how many take the day. Yeah, so this is, just ignore this. It should be swapped. It should be day over the supercomputer. And then that's 10 to the negative 17 equals 10 to the 23 computes a day, which another way to think of computes is some formal like if then statements. So say like this is 10 to the 23 if then statements a day. That's one way to think of it. And let's see, there's one more thing. I think we got stuck on. Oh, yeah, so I I hope I learn I can get this better in the future, but 8.4 times 10 to the fifth. The textbook says to round it if it's above 3. This number's above 3. So that's about 10 to the 6 order of magnitude. Anyways, let's get into today's chapter. So we have some important measurements. This is length, mass, and time. These are the fundamental. So this textbook will stick with 3 measurements. So physics, it's important to build models. That's how we describe the universe. Um, so let me get a new, oops. So touch this, get a new canvas. Okay. So physics, we have a theory. We're going to name it T. And a theory has a set of laws. And so for all, so for all L in T, there exists uh, a combination of um, quantities, so or variables, or like meters per sec, meters or seconds. What's second? It's like a variable kind of. So we'll put a combination of V, and it can go 1, 7. Let's do colons. So for all the laws that are in our theory, because this is our set, a theory is a set of laws, and the laws are a physical action that we observe. For all laws in our theory, there exists a combination of variables, which would be so like a variable could be length in meters. It could be your V1. It could be oops. I don't want to zoom. Okay. What if I just do a new one? No, I'll keep it there. I think you guys can see that. Sorry about that. Okay. Say I'm working with 2 different tabs, so if I click one, it messes up the other. So kilogram, mass, kilogram. So V1 could be mass, or I'm sorry, length in meters. V2 could be your kilograms, and V3 could be. So for this volume of physics, we're gonna stick mostly to these 3 variables: meters, kilograms, seconds. There's more, and it'll explain the book here. So quick note, these standard models, when you see one that has like an atom in the center with an electron moving around it, it's never like a perfect circle. It just makes it nice to model. It can be it's hard to know where an electron is, and it could fall out a more elliptical orbit. And then there's also another way of thinking about it as, say a atom is here, and let's say it's in the middle of a 3-dimensional plane. So our atom is at the origin of this 3-dimensional plane. So think of the 3-dimensional plane of turned into small cubes. So you might have a cube here. I'm sorry. So an electron could be in any cube. That could be like its probability state, if that makes sense. That's another way to think about it. It might not be right, but that's something I've considered. So yeah, theory helps to explain patterns in nature. Law uses concise language to describe a generalized pattern. So the most famous law is force equals ma. So you need calculus and maybe linear algebra to understand force equals ma. All right, so let's keep going. So here we go. Physical quantities. This is the fundamentals of physics. We use the standard units. Instead of English, the standard units have base quantities of meter, mass, time, length, mass, and time. And that's in meter, kilogram, seconds. So we're not using feet, we're using meters. We're not using pounds, we're using kilograms. And we're not using something else. You know, I mean, this is kind of universal, seconds. These other four will be in later physics books. And so I said laws in the theory are a combination of these variables. So what that means is you can have meters per second. You could have meters per second squared. Not every combination works. It has to make intuitive sense. You can have maybe kilograms per meters. That might be like something like force, like you're moving a mass per like a car is moving. Well, that would still have a time element. So I feel like most things in this book will probably have a time element. The example I was trying to get to is you could have like electric current A over mole. That would be your Faraday constant for, I think, it might be electric density. And then you could have A over mole cubed, which would be like electric density for a three-dimensional object. And there's the link somewhere. Here it is. And it shows you like these are the kind of the common variables. This is time. I know you can't see the left column, but this is length, and mass, M, electric current, I, thermodynamic temperature, T, amount of substance, N, luminous intensity, IV. And then there's this, which kind of tells you how these how like sensible, like what makes sense combinations of the units can be. So here we have joules, Newton, coulomb, degree. These are the common ones you might have heard of: volts, Pascal, watts, hertz. The hertz one's kind of interesting. I know I've heard of hertz. It usually refers to like sound, or like a processor might be like, or your 5G might be 5 gigahertz. I didn't know it was a time variable per se. I know it had to do with how rapid like a sinusoid fluctuates or repeats. But yeah, we have conductance, capacity, um, Kelvin, mole, ampere, kilogram, meter, second, candela. Candela is probably the one no one has ever heard of. I don't ever heard of that one. So yeah. So I wonder how big a cable is. One cable. So our meters, kilograms, seconds, these are our base quantities. This book's only going to worry about those 3 meter, kilogram, and seconds. And from those, you can get derived quantities like amperes per mole cubed. And it gives more examples here. Derived quantity can be square meters. This is using 2 base quantities. And then you can also combine them. I'm sorry, I think I'm getting the hiccups. Then you can also combine them to get meters per second. So not every combination works. It has to have has to make intuitive physical sense. So let's see. The second, it's a long history, 86,000 seconds in a day on average. So seconds are important. I wonder if they'll convert it to light seconds as well. So time is redefined. The second was redefined as the time required for 9 million observations. 9 million observations of a cesium atom. All right, so these are atomic clocks. This is how you get like the kilogram. It might be like some metal that they use to weigh. So there's like a physical substrate that these variables, should I call them variables? Should probably just call them units, right? So we'll just make it a U. These units. Let's see, meter. Talks about the history. Kilogram. So yes, this was talking about kilograms defined by platinum iridium cylinder. You can see it's got like some kind of controlled environment to get very precise measurements. So SI units part of the metric system. That means they're base 10. So they scale really well with log graphs. Yeah, it's easier to visually um, describe them. So centimeter. Let me give me some more space here. So centimeter, centimeter, 100. So 1 cm equals 10 to the negative 2 meters. Kilometer is 10 to the 3 meter. Kilometer. All right. I got confused with kilogram for a second. Megagram. 1 megagram equals 10 to the 6 grams. And 1 nanosecond is 10 to the negative 9 seconds. So here we have prefixes. So what's the most common you've probably heard of? Peta. That's a big word for where where computation is now. A lot of people will say petaflops, which probably means 10 to the 15 computes per second. Tera, you might think terabytes. That would be 10 to the 12 bits or bytes. So let's clarify. Terabytes is that 10, 12 bits or bytes. So if you recall, I think bit is either a 0 or 1, and then a byte is a string of 0 and 1s. So you might have a 8-bit byte, so it would have 8 integers, I think. So in the international, a terabyte is a byte. Is in the binary system computing storage officer is part of 2, so a terabyte might be 2 to the 40 bytes. So it's just slightly larger. So what is a byte? It's a basic unit. Okay. So interesting. We have another unit, a byte. So 1 byte. Textbook probably won't use that, but that's not a physics. That's an information theory value or measurement quantity. 8 bits, like I said, consists of 8 bits, and each is 0, 1. So yeah, bytes are 8 eighths. Okay, makes sense. Giga. Let's see, kilo, milli, yeah, milligram would be 10 to the negative 3 grams. Only rule is you cannot double them up. For example, if you measure it in petameters, it's not proper to talk about mega gigameters. Okay. Let's see. Kilogram, but the metric prefix needs to be applied to the gram. Okay. So, oops. So it's 1,000 kilograms. It's 10 to the 3, which is 1,000, which is 1 moved over 1, 2, 3 places. 1, 2, 3. So the decimal is moved over 3 places. 10 to the 3. So 10 to the 3 kilograms is written as 1 megagram. 10 to the 3 kg is 1 mg. So again, these are our standard quantities. So again, 10 to the 6, you look at what's 10 to the 6, that's mega. So you want to say megasecond, you might say picoseconds, you might say nanoseconds, but megasecond, you could say it, but there's like a sort of a convention to how these are used, I think. Yeah, nanosecond, microsecond, millisecond. I think millisecond is the most common if you are into computer scripting. That's 10 to the negative 3. Alright, so what is this example? Restate the mass 1.93 times 10 to the 13 kilograms using a matrix prefix resulting in a numerical value bigger than but less than 1000. Okay, so you want a numerical value bigger than 1 but less than 1000. Okay, so basically they want something like 193 like megagrams or something. I think that's something what they're trying to say. So 10 to the 13, that would be 10 to the 13, that is so let's do our, remember we talked about we can kind of estimate it, so let's give them an estimation. So let's give 10 to the 13 kilograms. We want to convert it to something different. So that could be 10 to the 12 plus 1. So we could say it's 1 times plus 10 to the 1, I'm sorry. So we could say it's 10 times okay, I see. We could say 10 to the 1. So we could just say it's 10 teragrams. Okay, I think that makes sense. Since we're, no, let's see if we're correct. Okay, with a factor of 3. So 10 to 3 is 1.9 times 10 to the 13 minus 10 to the 3 grams. It's 1 times 10 to the 16 grams. Okay. So 10 to 3 kilo K, that's the prefix, plus 10 to the 13 grams. So that's 10 to the 16 grams. So peta, between peta, exa. If we use peta, then we find out 1.93 times 10 to the 1 petagrams. So 16 is 1 plus 15. Exa, we could say that's x negative 2. So yeah, these exercises will help us solidify what they're talking about here. I get the point, but I haven't exercised it enough to be really comfortable. I'm sure it might be the same for you as well. So it's easy to make silly arithmetic errors when choosing. So always check final answers match the numbers we start with. Put numbers aside to identification. Count powers of 10. All right, so the prefix has its own 10 to the whatever. Okay, so let's check our understanding. 4.79 times 10 to the 5 kilograms. So what is this saying? 4.79 times 10 to the 3 times 10 to the 5 grams. So it's also saying 4.79 times 10 to the 8 grams. So let's look at our chart. 10 to the 8. So the closest would be 4. I can do, oh man, I can do 4.79 times 10 to the 6 times 10 to the 2 grams. So best I can do is 4.79 times 10 to the 2. Let's use a capital M, megagrams. Mega with a capital letter. Okay. I think that works. So unit conversion. Use conversion factors to express the value of a given quantity. Convert 80 meters to kilometers. Okay, so 80 meters to kilometers. So what is this first saying? This is 8 times 10 to the 1 meters. And we're converting this to 8 times 10 to the n kilometers. So if you recall, meters are our base. So it would be 8 times 10 to the 3 for kilometers. And since I think it would be -3 because I know we'd have to move the decimal place. Maybe. Maybe not. 80 meters to kilometers, so we know kilometers is a 10 to the 3. So let's consult the book. What are they doing? It says 1,000 meters and 1 kilometer. So 80 meters equals, okay, so we have 80 meters over 1, and we want to convert it to 1 kilometer. So this is Yeah, I don't like how this book's teaching this. Um, okay, this is what I started doing. 8.0 times 10 to the 1 meters equal to 8.0 times 10 to negative 2 kilometers equals 0.08 km. So what happened here, converting to km, so we did times 10 to the 3. What we really did was 10 to the 1 divided by 10 to the 3. The distance from the university to home is 10 miles. Okay. So it's distance from university. So we have a point U. Home, this distance is 10 miles. And takes 20 minutes. So the average speed is meters per second. So that would be 10 over 20, 1/2 miles a second. Equals half a mile per second. We want to convert 1/2 a mile. So 0.5 mile to meters. So there's 1609, so that's 804.5 meters a second. Let's check our answer. Oh, and we also forgot to convert this to seconds. So minutes, a minute over 60 seconds. So we're gonna do 804.5 divided by 60. That should be 2.6 meters per second. We're not really getting that. So we did get 0.5 miles a minute. So 0.5 miles a minute. And we know there's 16 1609 meters in a minute in a mile. Okay, I see. 1609 divided by 60. Okay, so did I mess up? I don't think I messed up something. Maybe the book's wrong. Let's see. 0.5 times 1609. It's 13. Okay, 1609 divided by 2. It's 804. Divided by 0.5. Okay, so I think I see what I did wrong. So 1609 divided by 0.5 is the same as saying 1609 divided by 1 divided by 2, which is the same as saying 1609 times 2 divided by 60. So I got that messed up. I did 1609 divided by 2 when it should be 1609 times 2. All right. So yeah, about 18 minutes left. Be sure to check your units are canceled correctly. Check the units, finance, make sure. So, okay. Check your understanding. Light. Travels 9. Is that pentameters a year? Here. 1 year is 3 times 10 to the 7 seconds. So it's basically asking what is 9 times 10. And let's look up our chart. P is 10 to the 15. And that's 3 times 10 to the 8. And that is meters a second. So let's check this. What is 9 centimeters a year as meters a second? Okay, I guess ChatGPT doesn't even know physics. Or maybe I just typed it wrong. Penta, I meant peta. Convert to side note. So we got about 3 times 10 to the 8th. So we did that right. Okay. Man, I'm sorry. Density of iron is 7.8 grams per cubic centimeters. The density of iron is 7.86 grams cm cubed under standard conditions. Convert it to kilograms per mass cubed. Okay. So grams to kilograms. So there's 1 kilogram. So that means 0.1 kilograms equals 10 to the 2 grams. 0.01 kilograms equals 10 to the 1 grams. 0.001 kilograms equals 10 to 0 grams equals 1 gram. All right. And what's our other rule? 1 centimeter equals 10 to the negative 2 meters. So that would be 10 to the 1 cm equals. So we're multiplying both sides by 10. So that would be 10 to the negative 1 meters. 10 to the 2 centimeters is 1 meter. And 10 to the 3 cm is 10 meters. Okay. So 7.86 times we want meters squared. So grams, let's convert grams. So if we do 0.001, that gives us our grams. That converts gram to kilograms. And then to convert so we'll divide by, so we got centimeters cubed, 10 centimeters cubed. All right, I'm getting stuck here. So let me try it the book's way. So we have 7.86 grams per cm cubed. So we want to convert this to kilograms per cubic meters. Okay, so we know there's 10 to the 3 grams in a kilogram, so these will cancel out. So now we have 7.86 kilograms over. So now we need to convert centimeters cubed to meters cubed. So we'll take, so how many, like the previous question, how many centimeters cubed are in so we want these to cancel out, so we want centimeters cubed on top, and we want some number followed by meters cubed. So the author does this. So okay, let's skip that. Let's just do 10 to the negative 6. Man, so I think the author is saying there's 10 to negative 2 cubic meters. Okay, so we still have the 10, so we have to keep the 10. So let's so we want to convert, so we're just converting grams cm cubed. So we know there's 10 to the third grams in a kilogram. So that the grams cancel out. So now we have 7.86 over 10 to the 3 times your kilogram over this. Okay, and now we want to convert it to, we want to convert centimeters cubed. We want to convert that to meters cubed. So we take centimeters cubed and I know they're kind of getting ahead of us on here, but so 10 to the negative 6 It's this exponential that's over the whole thing that's really throwing me off. So all right, we got 5 minutes. So did we learn anything? This is harder than I thought, keeping track of everything. So let's see, check your understanding. Let's see if we can do this before we call it. So diameter of the Earth is of order of 10 to the 7. So the order of magnitude of a surface area is so it equals the diameter of Earth, and then 10 to the 14 is the surface area of the Earth. What is that? So what is 10 to the 14 meters squared? I probably should have added the units on these. My bad. So what's 10 to the 14 meters squared in km? All right, so we know km is 10 to the 3 meters. So it should be 10 to the 17 meters. Square meters. Similarly, we have 10 to 7. Square it to get our 10 to the 14. So let's check our understanding. 10, 14 meters to 10 to the 14 meters squared divided by 10 to this 1,000. So they're getting 10 to the 8 kilometers squared. Is that even what they asked for? So I'm not sure if the language model's right or we are. Why wouldn't you just add 10 to 3 meters? We're dealing with area, and the conversion involves squaring the conversion factor. Okay. So there's the two-dimensional component makes this a little bit more complicated. So I'll try to learn more about converting. I think more about it, and hopefully next lecture is a little bit more smooth. So I'll see you guys next time.